Here we have a question. Let f of x is equal to x square. A is the closed interval 0, 4. B is the closed interval minus 1, 1. Find f inverse A and f inverse B. And you got to check whether f inverse A intersection B equal to f inverse A intersection f inverse B. You also got to check whether f inverse A union B equal to f inverse A union f inverse B. Now, when you look at this function, f of x is equal to x square, and nothing is said about the function. That means f from where to where, it is not specified. So as it is not specified, we can consider that it is from R to R. That means from the set of real numbers to the set of real numbers. Now, here you are given A is equal to closed interval 0, 4. You got to find f inverse A. So as the function f of x is equal to x square, f inverse A means the set of all real numbers whose square lies in closed interval 0, 4. That means whose square lies in between 0 and 4. So the real numbers whose square lies in between 0 and 4 are the set of real numbers from minus 2 to 2. That means the closed interval minus 2, 2. Now f inverse B means the set of all real numbers whose square lies in between minus 1 and 1. We know that square of any real number is positive, so there will not be any elements between minus 1 and 1. So you got to check all the real numbers whose square lies between 0 and 1, taking the positive part of this interval. So the real numbers whose square lies between 0 and 1 are the real numbers in between minus 1 and 1. So closed interval minus 1, 1. So this will be f inverse B. So f inverse A, we have found it as closed interval minus 2, 2. And f inverse B, we have found it as closed interval minus 1, 1. Now the things required here, we have to check whether f inverse of A intersection B equal to f inverse A intersection f inverse B, and f inverse of A union B equal to f inverse A union f inverse B. Now we have f inverse A and f inverse B in hand. So we will find the union and intersection of f inverse A and f inverse B. So f inverse A intersection f inverse B, that is the intersection of the two intervals minus 2, 2 and minus 1, 1. So when you look at the common region of the closed interval minus 2, 2 and the closed interval minus 1, 1, you can see that the common region to both the intervals is the closed interval minus 1, 1. So the intersection f inverse A intersection f inverse B will be closed interval minus 1, 1, and the union f inverse A union f inverse B will be closed interval minus 2, 2. Now you got to find a few more things. You need A intersection B, f inverse A intersection B, A union B, f inverse A union B to complete the question. So first we will find A intersection B. A is closed interval 0, 4 and B is closed interval minus 1, 1. So the intersection, that means the region common to both A and B, closed interval 0, 4 and closed interval minus 1, 1 is closed interval 0, 1. So to find f inverse A intersection B, you have to find all the real numbers whose square lies in between 0 and 1. That means the closed interval minus 1, 1. And similarly, A union B is the union of closed interval 0, 4 and closed interval minus 1, 1. So A union B will be closed interval minus 1, 4. A union B will be closed interval minus 1, 4. Now before saying anything about this, we will go back. So here f inverse A intersection B is closed interval minus 1, 1, and f inverse A intersection f inverse B is also closed interval minus 1, 1. So from this two we can see that both of these are equal. So f inverse A intersection B is equal to F inverse A intersection F inverse B. Now, we have already seen that A union B is closed interval minus 1, 4. Now, to find F inverse A union B, you have to find all the real numbers whose square lies in between minus 1 and 4. In fact, whose square lies in between 0 and 4. So, if you look at all those real numbers, you can see that these are the real numbers lying in between minus 2 and 2. That means closed interval minus 2, 2. So here we have a F inverse A union B is a closed interval minus 2, 2. And we also have F inverse A union F inverse B is closed interval minus 2, 2. So from both of these we can see that F inverse A union B is equal to F inverse A union F inverse B. And this completes the question. We shall now move on to the next question. Show that for an arbitrary function g from R to R, it is always true that G inverse A intersection B is equal to G inverse A intersection G inverse B, and G inverse A union B equal to G inverse A union G inverse B for all sets A and B subset of R, set of real numbers. Now, to prove the first part, G inverse A intersection B is equal to G inverse A intersection G inverse B, we know what to do. We have to first prove that G inverse A intersection B is contained in G inverse A intersection G inverse B, and we have to also to prove that G inverse A intersection G inverse B is contained in G inverse A intersection B. So this, take it as the first equation, and this take it as a second equation. Now we shall prove equation number 1. For that, we will take an element of G inverse A intersection B and show that that element belongs to G inverse A intersection G inverse B. So I am taking an element X in G inverse A intersection B. Now X element of G inverse A intersection B implies that G of X is an element of A intersection B, which means that G of X is an element of A and G of X is an element of B. Now G of X is an element of A implies that X is an element of G inverse A, and G of X element of B implies that X is an element of G inverse B. Now here we got X element of G inverse A and X element of G inverse B, which means that X is an element of G inverse A intersection G inverse B. Now we started by saying that X is an element of G inverse A intersection B. Now we got that X is an element of G inverse A intersection G inverse B. So this implies that G inverse A intersection B is contained in G inverse A intersection G inverse B. Now to prove the converse part, that means to prove that G inverse A intersection G inverse B is contained in G inverse A intersection B, we will take an X element of G inverse A intersection G inverse B and show that this X is an element of G inverse A intersection B. So let X element of G inverse A intersection G inverse B. This means that X is an element of G inverse A and X is an element of G inverse B by the definition of intersection. Now X element of G inverse A implies that G of X is an element of A. Similarly, X element of G inverse B implies that G of X is an element of B. Now we got that G of X is an element of A and G of X is an element of B This means that g of x is an element of A intersection B also. So now g of x element of A intersection B will imply that x is an element of G inverse A intersection B. So we started by saying that x is an element of G inverse A intersection G inverse B. Now we got that x is an element of G inverse A intersection B, which implies that G inverse A intersection G inverse B is contained in G inverse A intersection B. Now from this and this, we can see that G inverse A intersection B is the same as G inverse A intersection G inverse B. Now to prove the same relation with union, that means G inverse A union B is equal to G inverse A union G inverse B, you can proceed in the same way. And I want you to try it as an exercise by yourself. Here we have a theorem which states that two real numbers A and B are equal if and only if for every real number epsilon greater than 0, it follows that modulus of A minus B less than epsilon. Now here you can see that there is a condition if and only if used in the theorem. So whenever if and only if is used, you can see two statements, one before if and only if and another one after if and only if. So here the first statement is two real numbers A and B are equal, and the second statement is for every real number epsilon greater than 0, it follows that modulus of A minus B less than epsilon. Now to prove this theorem, we have to show that if 1 is true, then 2 is true. This is the forward direction, and in the backward direction we have to show that if 2 is true, then 1 is true. So these are the two things required to prove this theorem. So first we shall see the proof in the forward direction. So in the forward direction, we will assume that the first statement is true. That means if A equal to B, then we have to show that for every real number epsilon greater than 0, it follows that modulus of A minus B is less than epsilon. And in the backward direction, we have to show that if the second statement is true, that means if for every real number epsilon greater than 0, if modulus of A minus B is less than epsilon, then we have to show that A and B are equal. That means A equal to B. First, we shall see the proof in the forward direction. So in the forward direction, we have to assume that the two real numbers A and B are equal. That means we will be assuming that A equal to B. So let A equal to B. Now if A equal to B, we know that A minus B is equal to 0. And so modulus of A minus B equal to 0. Now modulus of A minus B equal to 0 means that modulus of A minus B will be less than epsilon, where epsilon is any number greater than 0. So this proves the second statement. This is a second statement. That means if you have A equal to B, then we have shown that modulus of A minus B is less than epsilon, where epsilon is any number greater than 0. So this proves the first part. Now to show the converse part, we will assume that for every real number epsilon greater than 0, it follows that modulus of a minus b is less than epsilon. Our motive is to show that a and b are equal. That means a equal to b. As a contradiction, we will assume that a not equal to b. If a not equal to b, then either a is less than b or a is greater than b. If a is less than b, then a minus b is less than 0. And if a is greater than b, then a minus b is greater than 0. So in either case, modulus of a minus b will be greater than 0. Now, as modulus of a minus b is greater than 0, we choose this value as epsilon naught. That means modulus of a minus b, we take it as epsilon naught. Now, modulus of a minus b equal to epsilon naught means that modulus of a minus b is not less than epsilon naught. So if it is not less than epsilon naught, this gives us a contradiction to the fact that modulus of a minus b is less than epsilon for every epsilon greater than 0. This contradiction arises because of our wrong assumption that a not equal to b. So from here we can conclude that a equal to b. So which proves our second part of the proof. So this ends the proof of our theorem. Here we have a question. Form the logical negation of each claim as a positive statement that avoids using the word not. So here there will be some claims given. You have to write the logical negation of each claim without using the word not. So we will see what are the claims given. For all real numbers satisfying a less than b, there exists an n element of capital N, which stands for the set of natural numbers, such that a plus 1 by n less than b. The next one, there exists a real number x greater than 0 such that x less than 1 by n for all n element of capital N. Next one is between every two distinct real numbers there is a rational number. So we have to write the negation of all these claims. So before going for the solution of all these claims, we will just recollect what we have learned in our previous classes regarding negation. Now here you can see a phrase for all, and here you can see a phrase there exist, and there exist is usually accompanied by the phrase such that, and for all is usually accompanied by the phrase satisfying. Now we know that the negation for all is there exist, and the negation for there exist is for all. Now in a claim there will be two conditions given. The first condition in this claim is in the first claim is a less than b, and the second condition is a plus 1 by n is less than b. So usually a statement will come like if the first condition is satisfied, then the second condition is also satisfied. So when we negate it, we have to say that if the first condition is satisfied, the second condition will not be satisfied. So here we have to negate like if a is less than b, a plus 1 by n is not less than b. Not less than b means greater than or equal to b. Now we will try to negate the first claim given. The negation for all is there exist. So here we have for all real numbers satisfying a less than b. So when we negate it, we will write there exist real numbers satisfying a less than b, or there exist real numbers a and b satisfying a less than b such that, because there exists is accompanied by such that, and here there exists an n element of n. The negation will be for all n element of n. Here such that usually comes with there exists, so we will not use the word such that. A plus 1 by n not less than b, that means greater than or equal to b. So here the negation for the first statement will be there exist real numbers a and b satisfying a less than b such that there exists an n element of n will become for all n element of n we have a plus 1 by n greater than or equal to b. Now we will look at the second one, b. There exists a real number x greater than 0 such that x less than 1 by n for all n element of n. So there exists changes to for all, and for all changes to there exist. Okay. So here when we write the negation, there exists a real number x greater than 0. The negation will be for all real numbers x greater than 0. This will change. The negation of this will be for all n element of n x less than 1 by n. The negation of that will be there exists n element of n such that x less than 1 by n will change to x not less than 1 by n, which is x greater than or equal to 1 by n. For all real numbers satisfying x less than 0, that is the negation of the first part here. Now the negation of the second part here is for all will change to there exists n element of n such that there exists will be accompanied by such that x less than 1 by n, the negation is x greater than or equal to 1 by n. So for all real numbers satisfying x greater than 0, there exists n element of capital N such that x is greater than or equal to 1 by n. Now we will have a look at the last one. Between every two distinct real numbers there is a rational number. Now what this claim tries to convey is that take any two real numbers on the number line. Between any two real numbers you can find a rational number. So however close it may be. So if I take like this, these two numbers very close, then even then you can find a rational number between them. That is what statement claims. Now when we negate that, we have to say that we can find two real numbers such that there is no rational number between them. So there exist two real numbers such that there is no rational number between them. So we cannot use the word not. So we will say that all the numbers between those two real numbers are not rationals. Not rationals means irrational. So when we negate it, we can say that there exist two real numbers such that every number in between them are not rational. That means are irrationals. So there exist two distinct real numbers such that every number between them is irrational.